Hello, this is Ms. DB, and in this lesson we are going to learn about vectors. This is Chapter 8, Section 6, and it might seem like, what do vectors have to do with the trigonometry and the triangles that we've been working with? But actually you'll see that we are going to use some of the skills that you learned in order to apply them to the vector problems. So our objectives are to find the magnitude and direction of a vector, and also to use vectors and vector addition to solve real-world problems. There's quite a bit of vocabulary in this section since it's a new topic that you probably haven't worked with before, although maybe you've seen it a little bit in physics if you took physics, or sometimes in physical science, like a 9th grade science class, you might see a little bit of this. But these are the different things that we'll be talking about in this lesson. All right. So what is a vector? It is a way to represent the speed and direction an object moves. So it's a quantity that has both length and direction. So if you're moving something, you can represent that movement, both the speed and the direction, by a vector. So a vector can be named as a directed line segment, and here's a picture. This vector here can be named by either AB, and you make like a ray above it with an arrow, or the book will use, it's kind of a funny arrow with just one little thing on it, which really means vector, but a lot of programs don't have that, so then you can use the ray symbol. And you could also name it with the little letter V. So it's a lot like a ray, that it has an initial point, a beginning point, and then it goes on forever, or not forever, but it goes to the terminal point. So it's not like a ray that it'll keep going. It has both our stopping points, because that represents the length that it has, which is it represents the speed and the direction by both the direction and the length of it. All right, so we can name it, go back for a second. I'm trying to remember if they have a special name for this, the way you're naming it this way. I guess it's just the directed line segment way. But this is the way we'll be working with it, called component form. So you can use your less than and greater than signs on the keyboard to make these kind of pointy brackets. The component form lists the horizontal, where you would normally put an x-coordinate, and a vertical, where you would normally put a y-coordinate if it was written as an ordered pair. And that's the change from the initial point to the terminal point. So in this picture, it doesn't matter, like, is this 0, is this 1, is this 2? We're not naming the coordinates. We're naming the change. So if we're starting here, it has moved horizontally 1, 2 from C to D, because D is up here. So it's moved over 1, 2 horizontally, so that's what this number is. And it's moved vertically from here to here. It's moved up 1, 2, 3. So that's the vertical component. So the component form is a real nice little shortcut way of writing it. We would just write 2, 3. Use the pointy bracket so we know it's not a point. All right, let's try this one. Here's the initial point. Here's the terminal point. We want to write that in component form. And again, it doesn't matter. We're not going to find the coordinates of H. We don't say this is 1, 2, 3, 4. That's not what you do. You're just going, how did this one move from here to here? If it moves to the left, we're going to use a negative number. Also, if it moves down, you'll use a negative. So the horizontal change from H to G is -3. The vertical change is +5 because it went up 5. So you write those little pointy brackets, -3, 5. Must have the brackets, and make sure you know when to use the negatives. When you go left or down, you use a negative. All right, so now this one, they're actually going to give us some coordinates. So the first thing you would do is you could plot the points so that you could see what was going on. Let me do a little quick sketch. So -8, 1 would be right here. I'm going to call that -8 and call this 1. And N, so it's starting here because M is written first. And then it's moving to 2, -7, which is about here. So this would be 2, and this would be -7 here. So what we have then is a vector that started up here and moved to here. So the horizontal distance goes from -8 to 2. So -8 to 2 is a difference of 10. And the vertical component, so it moved to the right, so that's a positive 10. The vertical component, it went down. It started at 1, and it went down to -7. So that's a difference of -8. So they're going to show you with algebra how to do this. You would subtract, you take x2 minus x1, comma, y2 minus y1. And when you simplify that, you get the same thing I did. So you can either graph it and figure out the horizontal and vertical change, or you can subtract the x coordinates and the y coordinates. But remember, we're not going to write it as a coordinate. We're writing it as the component form of a vector with the pointy brackets. Okay, this is just says you need to write the component form. So find the change from the horizontal from here to this point, and then find the vertical change. They're both going to be negative because you're going left and down. So you'd write that as -3, -4. So component forms are not too bad. Here's another example. You can pause the video and try this one, and then check and see what you get. So for this one, you should have got 7, 1 for your component form of the vector. All right, next thing we're going to talk about is magnitude. The magnitude of a vector is its length. The magnitude of a vector is written by, those look like absolute value signs, but that's the magnitude of vector AB, or the magnitude of vector V. What's your vector, Victor? When a vector is used to represent speed in a given direction, the magnitude equals the speed. So I said that it will talk about the speed and the direction. The magnitude is the speed. So if a vector represents the course a kayaker paddles, the magnitude of the vector is the kayaker's speed. All right, so what we're going to do is we're going to draw this on a coordinate plane. The origin, unless they tell us otherwise, the origin will be the initial point. Okay, so we'll start at 0, 0 for our initial point, and then the vector, -1, 5, if I move from here, I would go a change of -1 on the horizontal and a change of +5 on the vertical brings me to this point here. Now, I wouldn't have to start at 0, 0. I could start anywhere and do a change of 1 on the horizontal would bring me to here, and then a change of 5 would bring me, I'm going to run out of room, but it would be here. So there's no rule that says I have to start at 0, 0, except that it makes the rest of this problem easier. Because to find the magnitude, we need to find the length of that vector. And to find the length, we can either use Pythagorean theorem or the distance formula. So remember that Pythagorean, we could make a right triangle here. And the Pythagorean theorem would say that a squared plus b squared equals c squared, and that's really what we're looking for is c squared. So you could say 1 squared plus 1, 2, 3, 4, 5 squared equals c squared. So that'd be 1 plus 20. So we'd get the square root of 26 for c. That's one way to do it. The other way is to use the distance formula. The distance formula says that you can subtract the x-coordinates and square them, and then subtract the y-coordinates and square them, and then take the square root of the whole thing. So here that is plugged in with numbers. -1 minus 0 for the x-coordinates squared is 1. 5 minus 0 is 5. Squared is 25. So again, we get the square root of 26, which is about 5.1. So this is really, you're just practicing finding the distance between 2 points using the distance formula. Okay, here's another example. Again, we will graph it, and I like to start at 0, 0, but you don't have to. It's not a rule. and then we will find the length of that segment. So you can either use Pythagorean theorem or the distance formula, and you should get the square root of 10, or that's approximately 3.2. That's to find the magnitude. Now to find the direction, here's where the trigonometry that we learned earlier in this chapter is going to come into play. The direction of a vector is the angle that it makes with a horizontal line. This angle is measured counterclockwise from the positive x-axis. In this example, that vector is 60 degrees. Let's look at some more examples here. I don't think I put any problems on the worksheet that have this method of naming the vector's direction, but if they called this north 30 degrees, then that would be from north on a compass point. So that is a possible, and you may see that in your future work with vectors. All right, so we've got a skier, and he has a vector. Let's draw the vector. We're going to start at the origin and go, our horizontal change will be 1, and our vertical change will be 4, so we'll end up right here. All right, next thing that we're going to do is from the x-axis, which is this one, the horizontal, we are going to figure out this angle from here to here. So from here to here, that's the angle we want to find out. So we are going to make a right triangle with the x-axis. So take your point B and go straight down to make a right triangle. Now we have a right triangle. The angle that we're looking for is right here. Okay, so now we got it. All we have now is a right triangle. We can find several parts of that. We know that this is a length of 1. We know this is a length of 4. I could find this side if I needed to, and I might have to. They might ask me to find the magnitude of this as well. But if they don't, then I could use the tangent function to find the missing angle, because tangent is opposite over adjacent. So the tangent of A is equal to 4 over 1, which means the inverse tangent of 4 is equal to the measure of angle A. So then you get your calculator out and you type in, the inverse tangent of 4, and you'll get it's approximately 76 degrees. So that is the measure, the direction of the vector, 76 degrees. All right, let's look at another example. First, we will plot on a coordinate plane the vector 7, 3, and we're going to use the origin as our starting point there, our initial point. Now again, you must make your right triangle with the x-axis, so go straight down, and here's your right triangle. The angle that we're looking for is right here. That will be the direction of the vector. So we need to figure out, what is this angle? Well, we know parts of this triangle. We know this is 3. We know this is 7. So again, we can use the tangent. We can say, well, the tangent of A is equal to the opposite side of 3 over 7, which means that the inverse tangent of that, of 3/7, will be equal to the measure of angle A. So then you get your calculator out and you find the inverse tangent. And I covered it up a little bit. Let me erase my stuff so you can read that. You get it's about 23 degrees, estimated, rounded. All right, another topic in this is a pretty simple one. You have equal vectors if they have the same magnitude and the same direction. They do not have to have the same initial point and the same terminal point. So in this example, these would both, you could do the distance formula or the Pythagorean theorem, and you could find that the length of both of these would be the same. Therefore, they have the same magnitude. You could also use the tangent function to find out that both of these little right triangles would have the same direction, because this will be the same angle. So therefore, they will be equal vectors. Two vectors are parallel vectors if they have the same direction or if they have opposite directions. It doesn't matter if they have the same magnitude. For in this one, They do not have the same magnitudes because you can see that this one is shorter than the other one. This would be 1 squared plus 2 squared. But they do have the same or opposite directions. So we could figure out this angle, that's the direction, and we could figure out this angle, and those two would be the same. So therefore, those are parallel vectors. If they have the same slope when you graph them, they will be parallel vectors. Okay, so this one asks you to find equal vectors and parallel vectors. And there might be more than one vector that it is equal to or parallel to. So for equal vectors, they have to have the same magnitude and the same direction. So the magnitude is found by taking the Pythagorean theorem or the distance formula, and these would both be 1 squared, and 1, 2, 3 squared, 1, 2, 3. So these are both 1 by 3, 1 by 3, and they both have the same angle. They both are over 1 up 3. If you took the tangent inverse of both of them, you would get the exact same thing. So JI and PO are equal vectors. They're the only ones that are. This one over here has a different magnitude because it would be 2 and 2. And this one over here is 1, 2, 3 by 1, 2. Okay? Now parallel vectors they can have the same or opposite directions, and they do not have to have the same magnitude. The two we just had, I, J, and OP, are parallel vectors, but also K, L, and M, N are. Even though they're pointing in different directions, they have opposite directions, and they have different magnitudes, but that doesn't matter for parallel vectors. And this is just an example for you to practice, so check this one out, pause the video, try it, and then check your answers. Alright, so for equal vectors, they have to have the same magnitude and the same direction. And which ones did you find for that? You should have gotten that only PQ and RS are equal vectors. Then for parallel vectors, remember that they do not have to have the same magnitude. All they have to have is either the same direction or opposite directions. And if they are equal vectors, they are going to be parallel as well. And then also XY is parallel to vector MN. All right, the next part is a little bit tricky. So for the resultant vector, that is when you add two vectors together. So you can do this algebraically, componently, with the components, or you can add them geometrically. So first of all, how come I had another thing here, it didn't show up? Let me just show you how to add them with components. If you add them with components, let's say you have a vector 3, 4, and you want to add to that 7, negative 1. All you have to do, if it's in component form, is add the two horizontal components together and add the two vertical vectors together. So 3 plus 7 is 10, 4 plus negative 1 is 7. 4 plus negative 1 is 3. That's it. That's all it is for components, so that's easy. Okay, and if it is geometrically, then what you're going to do, if you wanted to add vector u plus vector v, is you put the initial point, the tail, of the second vector on the terminal point, head of the first vector. So if I want to add vector u plus vector v, I place vector v so that the initial point is right at the end of vector u. And then you find this distance from these two together. You basically draw a diagonal line connecting this one's initial point to this one's terminal point. So let me demonstrate. Here's the adding vectors with their components, but we already talked about that. Okay, so here's an example with line segments. If you have vector u, this is going to be hard to do because I don't have a good, and vector v, and you want to add them together, you would take vector v and you would slide it up, and you would put this initial point right here. And then you would draw the exact same vector. I'm going to try. I don't know if I got the slope exactly right. Yeah, that's pretty good. And then, so all I did is I took vector v and I moved it up, and I put its initial point at the terminal point of vector u. So I moved it. It's not here anymore. Now you connect. Let me get a different color pen. Right here, I would connect these two, the initial point of u to the terminal point of v, connect those, and then you can find the magnitude and the direction of the resulting vector. All right, that's what you're going to do. Now, on the worksheet, there's only maybe one of these, and it's kind of a bonus kind of thing. These are a little bit tricky. All right, an airplane is flying at a constant speed of 400 miles per hour at a bearing of north 70 degrees east. At 60 miles per hour, a 60 mile per hour wind is blowing due north. What are the plane's actual speed and direction? So we have two vectors going on. We've got the airplane flying and we got the wind blowing. So we are going to make a sketch. It doesn't have to be perfect, but here's our sketch of our airplane first of all. Now it said 70 degrees north, which really means 20 degrees from the x-axis. So we sketch our plane in, and it's the red line right here. Now we're going to put the wind. Whoops. Where did the wind go? Oh, the wind was going, I didn't even see it there. The wind is blowing straight north. Okay, so that's this one right here. So what we're going to do is take that vector and put it on top so that this one will go right here. So we're going to move that on top of that. Don't they show me a picture of it? I wanted a picture. And there's examples in the book for this as well. So now my new vector, my resulting vector, would be that thing right there. All right, so in order to do this problem, you're going to write the vector of the airplane in component form. The airplane's vector has a magnitude of 400 miles per hour, and it makes an angle of 20 degrees with the x-axis. So we had that right triangle of 20 degrees here, and this was 400. So we can find, I'll call this x, and I'll call this y. We can find x and y using trigonometry. So the cosine of 20 degrees is equal to x over 400, and then you multiply both sides by 400 to get that x is about 375.9. Then we'll use the sine of 20 degrees, which will be y over 400, multiply both sides by 400, and get that y is equal to about 136.8. So now we can write this vector in component form, which is 375.9 and then 136.8. All right, next we are going to write the wind vector in component form. This is much easier because it's going due north, it's going straight north, so it's just 0, 60. Now we have, well, now they say to sketch the resultant vector AB, which I already did. And then you can add the components of the airplane's vector and the wind vector together. So now we will have, here's our plane plus our wind. And I said that all you have to do is add the two horizontal parts together and the two vertical parts together. So your resultant vector in component form is this. And then the magnitude of the direction of the resulting vector would be, if you were to graph that point, basically, on the coordinate system, and then you could find the distance from the origin to that point, which turns out to be 424.3 using the distance formula. And then you can find the angle using tangent like we did before. And the inverse tan of 196.8 over 375.9 is about 28 degrees. So when I sketched, where did it go? When I sketched this, they're saying that's what we found then. We found this with the distance formula, and we found this with inverse tan. And that's how you would do a problem like that if you want to give that a shot. That is a trickier problem, but the rest of the worksheet is quite straightforward and not tricky at all. So try that one if you're up for it. If not, I believe I put it as a bonus question. And there's an example in the book too that you can follow along with if you need a little more assistance. All right, that's it. Thank you very much and have a wonderful day.